Welcome to lecture 46 today. We will continue our discussion with bipolar devices. If you recall, we talked about base and emitter design in the last lecture. We talked about the base resistance and current crowding. Today we will talk about collector design, and we will move to a heterojunction bipolar transistor from there. Okay. But in between we also talk about the basic BJT fabrication technique. So we will see how much we can cover here. So to the whiteboard here. So the collector in the schematic here, you see a BJT, silicon BJT, and you can see that this is your emitter, this is your base well, of course you make a base contact here, and then this is a collector. Now there are some components of the collector design. You see this black part, it is directly below the emitter. You see this is your intrinsic collector. People call it just the collector in textbook. This is the intrinsic collector, the active collector below the emitter doping. To make a good contact, you need a highly doped n-type region. That is why this is your highly doped n-type region. Can you see that? N plus. It's called the sinker region, or called the reach through region. This is a highly doped n plus region, so the collector can make a good contact with lower excess resistance that comes here. Okay, it's a highly doped region. The other part is this is highly doped region, and this is a subcollector because it reduces the resistance. Okay, so this is a subcollector that comes here. This part, maybe I will use a blue color here. This part is lightly doped. Sorry, this part is lightly doped. Can you see that? This part is also lightly doped. Why? This lightly doped region actually reduces your base collector capacitance, because this is your collector, okay, and this is your base. Okay, so this base, and if you look at this part, this is a part of the collector also. This is the n minus part. It is lightly doped to reduce the base collector coupling capacitance. Okay, so that, and also it helps improve the breakdown to some extent, because it will, otherwise if it is highly doped, then this side you will have a breakdown that is happening. Laterally it will break down. Okay, of course this is the true intrinsic collector, and the thickness and the doping will affect many things such as the Kirk effect and the breakdown typically. Okay, and that is all pretty much is about it. You have the sinker region or the reach through region, you have the active region, you have the lightly doped region, and you have the subcollector region. These are the 4 parts of the collector. The collector doping, the collector thicknesses, that is a part of the collector design. You know that the Kirk effect directly depends on the collector doping. The threshold for Kirk effect we talked about is directly proportional to collector doping. Okay, and so the collector doping should be high in order to enable a high Kirk threshold, but a higher collector doping also leads to premature breakdown. So it is a conflicting requirement, as I have already told you many times. Typically your base widening becomes appreciable when your current density is exceeding 1/3 of the Kirk threshold. So if your Kirk threshold, just giving an example, if your Kirk threshold is 100 milliamp, that is the ultimate limit, even at 33 milliamp you will start to see base widening. The base push out effect will start becoming observable, although it may not kill completely, but it is observable. So your limit is then 33 milliamp or something like that. Okay, the absolute limit is 100 milliamp, and modern devices have to operate at high currents. So collector doping, a high collector doping helps push the Kirk effect. Okay, but a high collector doping also leads to low breakdown. Okay, a high collector doping also leads to low breakdown, and it also leads to a high base collector capacitance. Okay, so if you remember, capacitance goes as epsilon by d, the thickness, it is the depletion. If your doping is high, then your depletion is low, and if your depletion is low, your capacitance will be high. If your capacitance is high, then your RC delay will be high, which means your tau will be low, which means your tau will be high, which means your FT will be low. So a higher collector doping is useful for pushing the Kirk effect higher, but it is terrible for breakdown, and it is very bad for cutoff frequency. So because it will increase the base collector capacitance. So one of the things people do is that people use like a retrograde collector doping profile, which means that the collector doping can change. For instance, it is like an eye layer between base and collector to sustain higher voltage. For instance, in the previous picture, this n minus region helps improve the breakdown laterally between the base and the collector. Okay, and you can sandwich an eye layer. You can see that this is your base and this is your collector. you have a collector doping which is lighter here, and then it can increase the other side, again it will decrease and stuff like that. So, you tailor the collector doping profile in order to kind of get a higher voltage as much as possible without sacrificing the Kirk effect too much. This is a part of the collector design. Okay. So, if you look at a modern base modern silicon BJT, and this could be useful also for RF application, but in general a modern scale BJT. This is how the schematic looks like, although the picture looks old, but it conveys all the useful information. This is your base, can you see that? This is your base, and this is your extrinsic base, where polysilicon, p-type polysilicon is used to connect the extrinsic base. It is p-type polysilicon, remember p-type polysilicon is used to connect the external base here, okay, p-type polysilicon. This is your emitter here, this top one, and the emitter you have polysilicon, and then you have n plus polysilicon, that is your emitter. This defines the emitter footprint. Directly below that you have the intrinsic collector, which is also called pedestal collector. It's a pedestal collector is the intrinsic collector where the doping is kind of reasonably high. This doping is not super high, but it is reasonably high to push the Kirk threshold higher. You do not want a terribly low Kirk threshold, that is why you use some doping which is optimal, neither too low nor too high, but somewhat high, so that the Kirk. Below that of course you have a highly doped subcollector to reduce the contact resistance. This is your if your collector contact comes here, then this is your collector sinker or the collector reach through region. These are deep trans isolation, and this black one is oxide here. This oxide can surround the deep trench filled with polysilicon. This is called deep trans isolation to isolate devices or even entire blocks of circuits. This is your shallow trans isolation. This is your field oxide. This is your field oxide. This separates the base and the collector. Can you see that? Maybe I will change the color here. This is your shallow trans isolation STI, which separates the base and the collector to improve the base collector isolation. This is your N minus region, I believe here, that also helps improve the base collector reduce the base collector depletion capacitance. This is a sinker region to reduce the contact the collector resistance. This is a subcollector that further reduces the series resistance, and this is a pedestal collector, which is your true intrinsic collector with appropriate and optimum level of doping here. Okay. This deep trans isolation I already told is for isolating devices and even circuits. Earlier p-type diffusion regions were used, but they are not used, they take a lot of area. So, deep trans isolation is great, it reduces a lot of area, it also reduces this capacitances, it's more expensive, but it's more increasingly adopted, of course, it's adopted universally now. The base contact that you are forming here is actually self aligned. What is self aligned? It's you do not have to worry about the alignment as much. You define a process such that the sidewall thickness of the dielectric, for instance, will determine the spacing between two electrodes, in this case base and emitter probably. So, the base emitter separation is this, that is defined by the thickness of the dielectric that you are going to use probably. In this case that could be an oxide. So, that oxide thickness on the side will determine the spacing between the base contact and the emitter contact, and that is your self aligned process. And the base contact here is p-type polysilicon, which makes a contact to the p-type base below. Okay. This is the universal process now, where the extrinsic base, the base on the outside the intrinsic region, is contacted by a metal polysilicon, with a polysilicon contact to a highly doped p-type base. Okay. And then you have to have good isolation between different components, that is of course obvious, but we will talk about more about this when we talk about silicon germanium HBT, because there we can discuss many of the things in more details. Why? Because silicon germanium HBT is more mainstream now, the BiCMOS process. It helps achieve better device or I would say the system performance. When you combine bipolar devices, silicon germanium bipolar devices with RF CMOS, if you combine them together, you tend to get more benefits for a same cost, okay, or you can reduce the cost for the same performance. So, people tend to go for BiCMOS, and that is why we will talk about in more details about silicon germanium rather than spending more time on silicon RF BJT, because this is on the wane. People do not use silicon BJT, pure silicon BJT as RF devices anymore, it is mostly towards BiCMOS, as I keep telling you. Okay. This is the fabrication flow that people have followed for modern BJT. Your epitaxial wafer of course will look like a P minus silicon. On top of that you have an N plus layer which will be the subcollector, then N minus epitaxial layer. Of course you have to have wells and things like that defined here, okay, but you have to do ion implantation or you have to do a diffusion to form the base and subsequently emitter, but before that The process starts with filling up with deep trans isolation. So, you will etch and form this deep trans isolation here. This is basically oxide, filled oxide SiO2, and this is polysilicon wrapped around it deep oxide that makes it deep trans isolation that separates devices. Okay. Then after that you make an ion implantation, for instance, or maybe diffusion in earlier days to make an N plus sinker region or a rich throw. This is your N plus sinker region. This part is you dope unimplanted, you dope it highly N type, and you also make a P type polysilicon layer here for the external base contact. It's a P type polysilicon layer here. There are many steps in between which we are skipping here, and there is an oxide spacer, that's oxide is deposited. You see this oxide spacer the thickness of the oxide spacer will determine the distance between the base contact and the emitter contact. So, the base P type polysilicon is enabled here to make a base contact. Okay. After that you will diffuse or I'll implant the P type here to form this P well. Can you see that? This is a P well. You will also form an N type pedestal collector. You will have another ion implantation, most likely to have a pedestal collector defined here, and then there is a base that is defined here. These are subsequent ion implantation steps to define these layers. Okay. This is the P type intrinsic base, and this is the P plus extrinsic base. Okay. And the contact is here. This is your P type polysilicon contact to the base. Okay. Finally you put emitter, which is your N plus polysilicon. Okay. So, the N plus polysilicon layer will be emitter. You can see that this is your emitter, but the actual footprint of the emitter is this, which will be like 130 nanometer or 90 nanometer, for instance. So, this is your polysilicon layer that is formed as an emitter, and then of course these are contact windows that are formed here to it will also be formed here to make contacts to the base. Okay. And then you will make a collector contact here, and then your fabrication is done essentially. This is how modern BJT structures are fabricated. There are many steps in between. We have skipped through many of them. We will revisit some of this when we talk about the HBT anyways. Okay. So, this is how the BJT was fabricated. Now, we will leave behind silicon BJT. As I keep telling you, modern RF circuits seldom use pure silicon BJT as much. It is migrating towards silicon germanium BiCMOS HBTs. Okay. So, before that we will talk about the basic concept of HBT, and we will focus a little bit on 3,5 HBT. When I say 3,5 HBT, I mean the compound semiconductor HBT, gallium arsenide based HBT or indium phosphide HBT. I do not mean gallium nitride based HBT, because gallium nitride based HBTs do not exist in the market, although academically there has been research, but commercially they do not exist. There are many problems with gallium nitride HBTs. Okay. Actually there is no wide bandgap HBT out there in the market yet. It's an area that needs more research and investigation, because there are many challenges in there. Okay. So, in HBT we will talk about the basics of HBT, we will talk about the base current components, we will talk about the graded compositionally graded bases, and we will talk about the collapse of current gain, ballasting, not ballasting, it's ballasting. It's a emitter ballast or base ballast that you put to prevent collapse of current gain actually, and then we will talk about some high frequency performance. Okay. So, the problem with a silicon BJT is that I told you the beta to a first order is given by the doping in the emitter divided by doping in the base. Okay. And this ratio, so your emitter doping has to be really high and your base doping has to be really low, but your base doping cannot be really low because your base resistance will be very high and that will kill your device. So, your base doping also has to be high. If your base doping is high, then your emitter doping has to be even higher, and if such high emitter doping is used, then your emitter band gap will narrow. Emitter band gap narrowing will happen because of high emitter doping. If your band gap narrows, then this beta will fall down sharply, because a narrower emitter will have higher intrinsic area concentration than a base which has the intrinsic area concentration of silicon. A band gap narrowed silicon emitter will have a lower concentration of emitter intrinsic area concentration, and that will give rise to a dramatically reduced beta, because the beta will also depend on exponential of that band gap narrowing, delta Eg by kT. So, exponentially, even a very small amount of band gap narrowing can lead to an exponentially lower beta, which is terrible. This is what this slide means. Okay. There is one more thing, by the way. When you are injecting electrons from the emitter to the base, you are also back injecting holes from the base to the emitter, and this is a useless component of current, because this comes out through the emitter contact, input contact. It does not contribute to the output current, and that is why it is useless. You want to minimize this. This is called IE of P, the emitter current which is because of backflow of holes, and this is your IE of N, which is your injected forward injected emitter current because of electron. So, the total emitter current is actually the back injected hole plus the forward injected end. You want 100% to be this and 0% to be this, but in reality the ratio of this and this depends on the doping, and that is why it is a sad state of affairs that in silicon BJT you cannot get a high beta because your emitter band gap narrowing will kill the beta, and your back injected current is more. Okay, that is very bad. So, the way to resolve this was to go to a heterojunction bipolar transistor where the emitter is a wider band gap than the base. So, your emitter, this is emitter n type dope emitter, and your base will be narrower than the emitter. The different band gaps are used. So, your base is narrower, this is your base. So, what will happen is that when you join them together, there is this huge delta EV or the valence band discontinuity. So, all the holes here when they try to back inject, they will see a barrier delta EV, and the back injection will reduce by e to the power minus delta EV by kT. That is a huge thing, because the delta EV, even if there is a say 0.3 EV, this is suppose 0.3 EV, then e to the power minus 0.3 by 0.026, that is more than around e to the power minus 11. So, which means the back injected component of hole is suppressed by e to the power 11 time. Now, E square is roughly 10, you can say. So, this is like 10 to the power 5 or 10 to the power 6, almost a million times. Your back injected current component is suppressed by almost a million times just by having 0.3 electron volt of valence band discontinuity between the emitter and the base. That is amazing. If your base back injected current is suppressed, that means the forward injected current is million times higher than the back injected current. That means for all practical purposes your emitter current is consists of 100% of the forward injected current and almost 0% of the back injected current. That is fantastic, and the beta of this will now depend exponentially on delta Eg by kT. So, a band gap difference between the emitter and base of even say 0.3 or 0.4 EV will lead to a beta of 10 to the power 5 to 10 to the power 6 times higher than a silicon BJT beta. Even if the emitter is extremely highly doped, such that there is band gap narrowing, the band gap narrowing will only be a small amount. The benefit you get from the difference in the band gap because of the heterojunction, fundamentally speaking, the band gap of the emitter is much larger than that of the base. The band gap narrowing of the emitter, the shrinking of the band gap of the emitter will be very small compared to the difference of the band gap between emitter and the base. That is why the band gap narrowing, although it will tend to reduce the beta, but the benefit in increase of beta due to the band gap difference due to in a heterojunction HBT will be far more overwhelming, resulting in an overall significantly higher beta like 10,000 for instance or 1,000. You can get incredibly large beta because of that. Okay, that is the beauty of heterojunction. So, here in this picture you are seeing a compound semiconductor, just a schematic of a compound semiconductor. This is the delta EV and this is the delta EC here. Electrons are injected, there is a notch, but it does not affect because the electrons will just go here and then come here. If you have an abrupt HBT, this is an abrupt junction, there is no graded junction, abrupt, then the back injected current gets suppressed by e to the power delta EV, as I already explained to you. And these different layers of the compound semiconductor have to be decided based on the band alignment, lattice mismatch, device performance, etc., etc. For instance, you can have indium phosphide emitter and an indium gallium arsenide base lattice match as an HBT. You can have aluminum gallium arsenide emitter base HBT. Okay. You can get really high speed operation, millimeter wave, hundreds of gigahertz of cutoff frequency approaching terahertz. In fact, there are terahertz cutoff frequencies with compound semiconductor HBT. It is incredible. You can get all these benefits with this with very high gain also, of course. Okay. So, what are the typical stacks that are used in compound semiconductor HBT? You cannot arbitrarily use things, but the common stacks that are used, and I am going by emitter base collector, is you can have L gas emitter, gas or graded L gas base, the band gap has to be narrower of course, and then gas as the collector, and this is your substrate. On a gallium arsenide substrate, you have gallium arsenide as the or L gas as the collector N type, gallium arsenide or graded L gas as the base and an L gas N type as the emitter. Similarly, on a gallium arsenide base again you can have indium gallium phosphide as the emitter, which is a larger band gap, gallium arsenide or graded L gas as the base and gallium arsenide or IN gap as the N type collector. Or on indium phosphide substrate, which is more expensive, but it can give you more degree of freedom in compositional tuning. Indium phosphide substrate you can do an indium phosphide emitter, or you can do an indium aluminum arsenide emitter, which is a wider band gap. The base could be IN gas or graded indium aluminum arsenide, and the collector could be IN gas or indium phosphide. Okay. Similarly, you can have this is a type 2 heterostructure HBT. We will see that indium phosphide substrate, on that you have an N type indium phosphide collector and you have an N type indium phosphide emitter, which are both larger band gap than the gallium arsenide antimonide. This is your P type base, which is narrow band gap, but this particular structure has a very unique advantage. It can launch the carriers into the collector in a very unique way. We will see that when next slide probably, but this is it's a very promising HBT. In fact, the record, I believe the record cutoff frequency exists for this kind of HBT only. So the reason in most of these cases the base is either written as gallium arsenide or a graded L gas is because you can either have an abrupt HBT, in which case the base will be say L gas or IN gas or whatever, or you can have a graded HBT. In graded HBT the base will be graded, and that is why it can be graded L gas or it can be graded IN gas, it can be graded indium aluminum arsenide depending on the particular stack that you are using. This graded HBT has two advantages. One is that it gives you an extra quasi electric field that I already talked about, a quasi electric field because of the graded compositional grading of the base. There is an electric field already in the base that will accelerate the electrons injected from the emitter even more on top of everything else. This is not observed in a silicon BJT because of the offsetting counterbalancing effects I already talked about of band gap narrowing and a doping graded effect, but in an HBT like a compound semiconductor HBT, the graded HBT actually helps accelerate the electrons. The second effect, this is the first effect, and it helps increase the cutoff frequency. The second effect with the graded HBT is that the back injected current, if you recall the last slide, this back injected current is actually suppressed not by delta EV, but it is suppressed by delta EG by KT, and delta EG is the total band discontinuity, delta EV is the valence band discontinuity. Delta EG is equal to delta EC, the conduction band discontinuity, plus delta EV, the valence band discontinuity. So delta EG is actually much larger, which means the back injected current suppression is even stronger in a graded HBT than in an abrupt HBT. Okay. However, in a compound semiconductor HBT you have to understand that the lattice mismatch can play a key role. Your layers should have lattice mismatch to an acceptable degree such that the layers do not relax and create misfit dislocation. Ideally you want them to be lattice matched, and you have a lot of material options to choose from, because you can go ternary quaternary alloy, you can play with the band gap, the electron affinity, the band gap tuning, the band alignment, etc. to a large extent. Okay. You can dope the base really high and reduce the base resistance, and you do not get a problem with the beta, because your emitter can be doped very high, or even otherwise your delta EG between the band gap of the emitter and the base will give rise to a significantly higher beta despite a high base doping. Okay. And you can choose a collector which has a reasonably high breakdown field such that the breakdown voltage is not compromised. In the base you choose a material which has a higher mobility and higher velocity such that you can get even higher cutoff frequency. You have the ability and the flexibility to tune and tailor properties of the material stack. The device performance can be optimized by bringing together best material that gives you everything best. The base has high mobility, high electron velocity, the collector has high breakdown, fantastic, and the emitter base junction will have a high discontinuity to enable a high beta. So you can get a high breakdown voltage in conjunction with a high beta, in conjunction with a high FT, without compromising much of the things, because you are selectively choosing material for emitter, base, collector based on the properties that you desire in each of the layers. It is not a common material. What is the price you have to pay? Cost, complexity of the material. You need MBE or MOCVD to grow, and it's a fairly complicated growth. That growth complexity exists, and also it increases the cost for sure. So you can use this only for really niche applications which your performance is really critical, such as military or space. You may not be able to use it for broadband commercial application where cost drives the application. Okay. This is the, I have to remove these things. This was the type 2 heterostructure that I was talking about, this particular thing, where your emitter is your indium phosphide. There is also a highly doped indium gallium arsenide. This is to reduce the emitter contact resistance. It's like a degenerately doped, highly doped n-type region to reduce the contact resistance, to increase the injection electrons here. So this is your emitter, and this is your base, very thin base. This is your gallium arsenide antimonide p-type base, and this is a type 2 heterostructure. You see there is a significant discontinuity here. Okay, and you can see that this is the collector, indium phosphide collector. When the electron comes here, it gets launched. This is a huge discontinuity, so electron get launched. We call it launcher. This effect is called launcher. Which effect? The fact that the base and the collector has this delta EC. When the electron is injected from here, it diffuses across the base, and then it sees an abrupt field here. It gets launched here, okay, energetically. That's your launcher. It's 0.15 eV, and this leads to really high speed application. I believe the record high HBT in terms of record high cutoff frequency is reported in this kind of heterostructure. Okay. So this is a very unique heterostructure that you can design, and this is a subcollector. Again, you can use a material with very high mobility, very high doping that gives you very high very low contact resistance in the collector. This material gives you pretty good mobility and velocity, but this indium phosphide is a wider band gap that gives you larger breakdown voltage, but you do not sacrifice that in the emitter because you have a highly doped in-gas emitter here. This kind of mix and match play is only possible in compound semiconductor. Okay. So with that we will conclude today's lecture here, 46, where we talked about we introduced HBT, we talked about the collector design, and we introduced HBT, the heterojunction bipolar transistor. Lecture 47 we are going to talk about further into compound semiconductor HBT, including collapse of current gain, ballasting, and also about high frequency operation of bipolar compound semiconductor HBTs. Okay. So thanks for your time. I will see you in lecture 47 next. Bye.